I'm going to talk about rainbow maths. So what I mean by that is I want to talk about some of the theory about how colors and rainbows work, both in your eyes and in your electronics, typoed that, electronics projects. So there's not really going to be any maths in this in the sense of formulae and things like that. So I'm going way more for concepts. So questions like how does brightness work? How do RGB LEDs make your eyes see color? How do you express colors in computer programs on your Pi and Arduinos and things like that? So at the end of it, there are no formulae in this talk at all. Okay, so the first bit I'm going to do is talk about brightness. So if you've got a starter project with your Raspberry Pi or with your Arduino, that one of the most common things that you do is a turn your LED on and off project, or blink your LED. And that's cool. It's pretty easy to do. You've got a GPIO pin, you can set it on or you can set it off, and your little red LED goes on or off. But what happens is sometimes you see a slightly more advanced project, people make their LEDs that somehow it's half brightness or dim or pulsing or something like that. And that's not apparent. It's not apparent at all. How do you go from on or off to making that happen? So one of the concepts there, I keep getting these waiting room messages. One of the concepts there is a thing called pulse width modulation. And what that means is, as the amount of brightness that I can get out of an LED, if I just want it half, I just turn it on half the time and off half the time. And on average, it's on half the time. That's not a really complicated concept. If I want it on 10% brightness, then I turn it on for full for 10% of the time and off for 90% of the time. And that averages to 10% on. Okay, so that's basically, if you have your program that flashes your LED, you do that. You turn it on, you turn it off, you turn it on, you turn it off. So if you run it at the time scales of 1 second on, 9 seconds off, it looks like an LED that is pulsing on for 1 second and turning off for 9 seconds. But you can make that faster. And what happens at some point, when you reach about 10 or 20 flashes per second, so you're on for 100 milliseconds, a tenth of a second, and off for 900 milliseconds, fine. If you carry on to being on for 1 microsecond, off for 9 microseconds, or that sort of scale, all of those on and offs blur into each other, and what you get is an LED that appears to be on dimly. Okay. So that's a thing called persistence of vision. That's a thing to do with your eye. So that's nothing to do with the LED. That's nothing to do with the electronics. If you were an alien that had a different visual system, you would potentially just see that as a very fast flashing light. It's the human eye sees that as a sort of blurred, faded LED. And you'll see that if you sometimes try and take pictures of LED-based stuff with your phone camera, it will look really, really weird. Stuff will be on and bright, and some stuff will be dim and whatever. And that's because the camera doesn't behave like your eyes. So what you're doing here is really using electronics to make use of how your eyes work. So I said 10 to 20 times per second. That's also why television is approximately 25, 50 frames per second. Hollywood movies traditionally were 24 frames a second, because that's the speed at which you can start doing this stuff, and all individual things start turning into this blur of motion. So two of the common LEDs, dot stars, I was just talking about with Andrew, and that's what I'm using in my bike. The other one is neopixels, which were the LEDs that were on the wall behind me when I was showing the bike. They're the more common one, I think. So neopixels pulse on and off about 400 times a second, so 400 hertz. And dot stars are much, much faster at about 20 kilohertz. So both of those, if you've just got an LED somewhere and it's not really moving, either of those speeds is well above that 20 times a second, 20 hertz that you need to get the persistence of vision. So you don't need to go for a static LED like an indicator light. You don't need to go above what neopixels do. That's fine. Where things like dot stars, higher speed become useful is things like my bike wheel, my persistence of vision bike wheel, where although you'll get persistence of vision with a 400 hertz signal, if the LED is moving, which on a rotating bike wheel, or I've made a wizard staff once, which you wave around in the air, 400 hertz turns out to not be fast enough for that. And the pulsing, it doesn't manifest that, it manifests as dots in space rather than the fading not working. Okay. So the way that you describe that is that if you've got dot star LEDs or neopixels, usually they accept 1 byte for their brightness. So a byte, for the purposes of this talk, byte is a number, an integer, a whole number between 0 and 255. Okay. So you might talk about an LED being 0% on or 100% on or whatever. When you're working with LEDs and in this 8-bit byte space, then you talk about being between 0 and 255 instead of between 0 and 100. So off is always 0. It's 0%. It's 0 out of 255. Completely on, 100% on is 255 out of 255. And halfway is about 128 out of 255. So that's always got to be a whole number. You can't say I want to be on 128 and a half or anything like that. So if you look at any of the libraries that interface, for example, in Python, that interface dot star LEDs or neopixel LEDs, they'll usually want a number that is in this range. So that's cool. If I want an LED that's half on, I can set it to 128 out of 255, and it's going to appear half as bright as a full-on LED, right? Turns out your eyes don't work like that at all. If you have an LED that's on 50% of the time, 50% brightness, your eyes really see it as almost as bright as a completely turned on LED. You have to go really the way down to not being on very much. So for example, on one of my LED projects, I'm on for something like 10% of the time, and I can only just tell the difference between that and a fully on LED. So there's downsides to that and there's upsides to that. On the upside, it means I can run my LEDs at 25% on, so 64 out of 255. And the LEDs seem almost as bright, but I'm only using 1/4 of the power because the LEDs are not on very much. So my batteries will last 4 times as long. On the downside, that makes it much harder to do visual effects because you can't do as obvious fading effects. You can't just ramp up a number from 0 to 255 and back down again. That doesn't look like the beautiful fade you might want. So here's an example. You might think if I just did 10 steps, I would go dark, lighter, 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 up to full on. But actually, if I go up 1 unit, say 10%, it looks almost fully on straight away. And then as I keep adding more power, it does get brighter. It does get noticeably brighter, but really that first step was where all the change happened. So that's not so good for doing stuff. And there's a process to fix that. It's called gamma correction. If you click on the link at the bottom, or just Google Adafruit gamma correction, there's lots of explanation there and lots of code, and I don't want to put formulas in here because I don't want to be talking about formulas. But it basically means there's a graph here of what your eyes perceive and what the LED is doing. So if the LED is on 50%, you perceive way more up here, way more than 50% brightness. And down here, when I said you just turn it on a little bit, just a tiny bit gets us really very far up here. So basically there's very straightforward formulas that say, I want it to look like the LED is on 50%. And it will say, well, actually, you need to have about 33% duty cycle in your PWM to do that. And if I want it to be on 10%, well, that's here. So you need to have hardly any turned onness at all. And that's called gamma correction. Okay, so we haven't done anything about colors so far. All I've talked about is brightness and how to do with brightness. Now I'm going to go into a different dimension and talk about colors and rainbows. So there's a picture of a rainbow, and we've got different colors of lights as we move across the rainbow. So light is basically radio. It's got a frequency. It's much, much higher. So BBC Radio 1 is at 97 megahertz. Red light is a radio transmission at 400 million megahertz. So if you turned your radio dial from 97 up the way to 400 million, it would receive red light instead of Radio 1. Okay, so red light is about 400 terahertz. That's a million megahertz. That's this end of the rainbow. And then violet is 700 terahertz. That's this end of the rainbow. Hopefully you can see my mouse cursor. So we go from 400 terahertz, 5, 6, 7 across here. So somewhere in the middle, that's going to be whatever, 500 terahertz. Yellow is 500-ish. Okay. So what's happening here is when we've got a pure color, it's a very specific, focused, single frequency of light. So separate from that, we've got RGB LEDs that you can buy NeoPixels or dot stars. And what's happening in there is an RGB LED is actually 3 LEDs. It's got a red LED, a green LED, and a blue LED. That's where the name RGB LED comes from. And each of those you can control the brightness of independently using PWM, just like I talked about in the previous section. But you get to do it for each of those 3 colors to get separately. So what you can do is mix those colors together to get different colors. So if I turn on the red LED and the green LED, you get yellow out of it. If I turn on the green LED and the blue LED, you get cyan out of it. Okay, and so you can fiddle with the levels of those 3 LEDs to get whichever color you want within reason. Okay, so if you take those 2 different slides I've said, they do not fit together at all. One of the slides says yellow is this very specific 500 terahertz radio wave. And the other slide says yellow is actually a mix of red lights and green lights at 400 and some other frequency. Okay, those explanations don't fit together at all. They're completely contradictory. And the resolution to that is that it comes down to how your eye sees colors. So humans have mostly what's called trichromatic vision. And what that means is your eyes can only actually detect 3 kinds of color. And they are roughly blue, roughly green, and roughly red. So if I'm shining a red laser pen into my eye, it will be sort of here, and it will stimulate. This is a response graph. So here are the 3 different colors that your eyes are sensitive to. It will stimulate the reddish detector of your eye, but it won't stimulate the greenish or the bluish detectors. So your brain will say, all right, that must be red light. If I send in blue light, it will stimulate this thing, the bluish detector, but it won't stimulate the other. And your brain says, okay, that must be blue light. If I send in yellow, yellow is going to fall in about here. And actually it will stimulate the green detector and the red detector about the same. So what happens is your brain says, oh, the green, my green sensitivity, my red sensitivity are both being stimulated equally. This must be yellow. I'm going to perceive this as yellow light. Okay? So the eye isn't directly detecting the frequency of this light here. It's saying, I'm looking for stuff that's almost green and stuff that's almost red, and yellow is kind of both of those. So what that means is I can fire yellow light into my eye, pure yellow light into my eye, or I can fire in an equal mix of pure red and pure green, and there's no way that your eye can tell the difference. Okay, because what's happening is that in either case, the red bit and the green bit of your eye are being stimulated equally, and that's the only thing that I can detect. So an RGB LED that is giving out yellow light is only giving out yellow light for beings that have human eyes, because you have to have this red, green, blue makeup in your eye that corresponds to the red, green, blue makeup of the LED. So if you're a space alien that detects light in a different manner, you wouldn't see yellow when a human sees an RGB LED giving out yellow. It just happens to be a trick of how your eyes work. Okay, the other slightly weird thing is we've got a rainbow here. It's linear, so it's red at one end and it goes through orange, yellow, green, blue, indigo, and violet, and then it ends. So it's a linear thing. But maybe you've encountered this. There's a thing called a color wheel, and we start red, orange, yellow, go green, blue, indigo, violet, but then suddenly it joins back on to the red again, which doesn't happen in a rainbow. So the rainbow is a physical manifestation of light. The color wheel is something that you perceive as a human with the human visual system. And what's happening is if you stimulate the blue bit and the red bits of your eyes and the blue bits of your eyes without stimulating green, your eyes treat that as a color that exists, but there is no real color that would stimulate the red and the blue without stimulating the green. So it's like this strange fake color that your eye sees as a real color, but that doesn't entirely exist as a pure color. And that is the little bit of the color wheel that joins the red end of the rainbow back round to the violet end of the rainbow somehow. And that's called the line of purple. And it's a strange construction that only exists, again, because your eyes only see a reddish, greenish, and bluish colors. Okay, so far I've talked about an RGB LED is 3 LEDs, red, green, and blue. You can control the brightness. You're going to pulse width modulate each one, probably using a byte for each one. Those bytes don't map linearly to the brightness that you will perceive. And so to get everything working right, especially the color mix right, you need to do gamma correction, which is that curve that I showed earlier. There's libraries to do that. It's a very straightforward calculation. And by specifying those 3 values, you can get roughly any color that you want. And because it uses 3 bytes, each byte is 8 bits. If you hear the phrase when people talk about 24-bit color, this is what they are talking about. They are saying a pixel in our image or whatever, we specify 24 bits of color for this pixel. I've specified 8 bits of red, 8 bits of green, or 8 bits of blue. Okay. So you need 3 values to specify any color, and RGB LEDs do red, green, and blue. that doesn't fit well with how brains perceive colors. So like I want to say, I want yellow. Well, yellow, I need to know because I know about these things that I need to mix a bit of red and a little bit of green. But that's not massively intuitive. So there's a different color model called HSV, which also needs 3 values, but the values are a little bit more intuitive. So HSV stands for hue, saturation, and value. So the hue is literally the color across the rainbow. So we've got red at one end, goes through orange, yellow, green, blue, indigo, violet, and then we start going through the weird line of purple to go back to red again. The saturation is sort of how washed out and white the color is. So fully saturated is the pure color, pure red, for example. As you get less saturated, it turns into a kind of whitey gray color. So that's another number. And then the V is the value, which is how bright or dark that color is. So we start black and we gradually brighten up. So if we had full red, pure red, this would go up to solid red, for example. So you can see in the last talk, for example, the depth measures were on the map. As the boat was driving around, the depth measures were presented. Ignore these two. They were presented as turn the depth into how far along this spectrum you go or back. So I can't remember which way. As the water got deeper, it got bluer, and as shallower, it got redder, or the other way around. So this is a lot more intuitive to how the human brain works to have parameters like this. But you still have to have 3 parameters to be able to describe any colors. There are libraries to do this. There's in the last month, I've used both Python libraries to do this and libraries in Rust, where I want to talk to an RGB pixel, but I want to feed in a number, feed in a color description using HSV. For example, because I want to make a rainbow, there are libraries that I can feed in an HSV value. It tells me the RGB value out, and then I can feed that to my pixels. There are loads of other color models available as well. An example, if you want to use old analog television, there's a model called YUV, which lets it be backwards compatible with black and white televisions, and all kinds of things. In general, all of them need to have 3 numbers to describe. To be able to describe any color, they have to have 3 numbers. But what those numbers mean is different. That's what it means to be a different color model. Okay, so that's some of the concepts to do with RGB LEDs. I've talked about pulse width modulation to control the brightness. I've talked about gamma correction, which is how controlling the brightness of the LED in a sort of scientific way doesn't match up to how your eyes see brightness. I've talked about this conflict between how RGB LEDs worked and how colors in science really work, and that's because of how you're human. I'm assuming you're all human. How your human eyes perceive that color. And I've talked about different color models, so that in your programs you can express things without having to use RGB. And that's the end of my talk. Does anyone have any questions?
Thank you very much. Very interesting. Thanks, Ben.
Yeah. Ben, one question. You on the slide that had hue, saturation, and value.
Yeah.
Unfortunately, there was a little bit that was grayed out. I think it might have been one of your.
Yeah. Zoom. Let me do a screen share again. Hold on.
Thank you. Seemed to suggest the value went over 255.
Yeah. So basically, I've just copied graphs. I've copied a load of graphics, and so what they are using here is degrees around the color wheel.
Oh, okay. Yes. So, I get it now.
So there's a whole one of the things that you'll encounter is there's no absolute numbers. It's not like I've got 3 pies or 2 pies. It is the numbers are all on a scale, and the various scales that you'll encounter, you might encounter a number between 0 and 1, so 0.2, 0.3, 0.4, and the range will be 0 to 1. Or you might sort of, that's the model that I tend to prefer using. If you're using bytes, then the numbers will go 0 to 255. In the case of this graph, they're using degrees, because they're imagining the color, they're imagining this not as a linear thing, they're imagining it as a wheel like this. So it very much makes sense to say that's 0 degrees, that's 90 degrees, that's 180. They're all equivalent. You just have to stretch the numbers and multiply them by a bit.
Okay, thanks for clarifying.
Yeah.
Ben, have you nudged your microphone? It's gone super quiet for me.
Oh. What about now?
Not a lot better for me. Anyone else got this?
Can anyone else hear me?
I
Yes, you're fine here.
You are a little quieter than you were at
Yeah, you perfectly.
Yeah, I don't actually know where the microphone is in my laptop. So as I move around, I might be covering it or not, or I might just be talking more quietly.
That's getting better. I wanted to ask you.
Oh, no, that's me just shouting. People always complain that I shout at my laptop, but apparently it's the right thing to do. Sorry, your question.
Yeah, keep up the shouting, Ben. It fits with the animation earlier. I wanted to ask you, you touched on the more or less logarithmic response of the eyes.
Yeah.
So that means that in order to dim a light, if I've got some RGB LEDs, then instead of sending them 255, I might want to go down a few steps on the scale, but because of it being logarithmic, I end up sending them 888 to get white that's dim.
Yeah.
That leaves me with almost no resolution for color. Do you know of any RGB LEDs that have a larger color range, that have, I don't know, 12-bit control or something like that?
No, I don't. But I've never gone looking for them. But it does frustrate me. So some of my own projects, I've done my own pulse width modulation, but only in black and white. So instead of my microcontroller controlling sending a byte to an LED, which is going to do the PWM itself, you can do the pulse width modulation yourself. So you could attach a red, a green, and a blue LED to a Pi or to a microcontroller and pulse width modulate it as fast as that hardware platform could do it. But it is still, it's very frustrating at the low end. I've got an LED beer bottle project where you can adjust the brightness with a rotary encoder, and right down at the dimmest end of things, it's still really noticeable how big one step is. Yeah.
The only solutions I know of, and I'm wanting to use an RGB matrix, is to use a discrete LED matrix where you've got an awful lot of wiring.
Yeah.
Or to use one of the NeoPixel or APA 102 matrices with a gizmo that's Adafruit cell. I don't know what the thing's called now, but basically it dithers colors, but it's not cheap, and it's not going to give that good a result, given that it's limited to dithering.
I think you hit the nail there with it. It's not cheap. My wife works in TV lighting, and she will always say that no RGB, the LEDs, no LEDs are created equal. So it's a fair crack in the NeoPixels, but in some, the red will be much more pronounced than the other. So trying to balance them up, and you find that in a lot of those kind of pro high-end fixtures, you get 7 or 8 different monocolor LEDs in order to color mix to try and make that a more predictable and consistent curve.
Yeah.
The dot stars do have 2 levels of brightness. You've got the individual brightness on each of the red, green, blue. you've also then got an overall brightness on the whole LED, which might give you a bit more control there.
Yeah, I read something bad about that. Not like bad as in evil, but bad that it didn't give you that much control. But I think maybe that was specifically, maybe that was specifically because it does a further PWM at a rate that was really bad for my bike wheels.
I think the global control is PWM, and I've got a vague recollection that the individual red, green, blue on the dot stars is not, it's analog, but I could be wrong.
Yeah. Yeah.
I'll look into that. Thanks.
Is there what other light, like the Neopix is obviously an obvious one, but there's other sort of light based projects and things like that. If anyone's playing around with those.
So the three things I've been doing with the LEDs tech-wise are NeoPixels and dot stars, which behave very similarly, and then PWMing LEDs myself off GPIO pins, just because I wanted to see if I could do it.
Yeah, but then there's
and
that
I
fiber type stuff, isn't there? I forget what it's called now.
What is that? What does it do?
I forget what it's called. It's sort of like more of like a fiber, or looks more like neon. I forget what they're called now. Does anyone know?
Oh, where you have a long glow wire.
Oh, EL.
The EL.
Luminescence.
Yeah, electroluminescence.
Yeah, can you actually change the brightness of those things, or are they just like a standard brightness? I've never actually used them.
I've played with them. They're very non-linear. You can't really get much brightness control.
Oh, really?
And no color control at all.
So they're either on or off, are they?
Yeah.
And even PWM doesn't do anything.
You probably vary the brightness with PWM, but the problem is that each individual thing is a big area, so you can't really mix colors.
Right. Okay.
Right. It would just be, you would just have, even if you could do it, you would just have brightness control.
Yeah, I'm just looking for a different display medium.
Lasers.
Well, I really like, lasers actually good.
I've seen some very good laser stuff, but I think it involved a lot of insurance and qualifications at sort of some guy showed up near here to do a stage show with vector graphics lasers, which involved a big emergency stop button that everyone's like, if anything goes wrong, anyone can push the emergency stop button. And he was a certified laser technician, but it was vector graphics lasers against a wall. And it was a laser that was just on continuously, I think. And then you could steer where on the wall it was pointing. So you could play asteroids and a lot of that 70s style video game with it. Which that's on my to-do list, but
there's a standard warning with all those things. Warning: do not look into laser beam with remaining eye.
Oh yeah. This was definitely that kind of device.
Like those projects where they use wall of water, and they're sort of making shapes out of the water droplets.
Yeah,
those are very cool projects.
Yeah. Oh, a strobe and dropping water.
Yeah, strobe and dropping water.
Yeah.
Very cool idea.
Mm.
Yeah, that's what I was suggesting for your next clock.
Yeah, it's not a bad idea.
Yeah.
So going to make a steam clock next. That's sort of what I'm thinking of.
Like in Vancouver.
Yeah, exactly.
Yeah.
Cool. Any other questions? Anyone? No? Thanks very much, Ben.
Yeah, cool.
Good fun.
Yeah.
Anyone have anything else they want to raise?
I showed my bike twice. I don't need to show it again. I can show you my beer bottle. Hold on. This was I need to move to a different room. So this is an 8085, which is the CPU used on a microcontroller that's used in an Arduino, the really low end version. I've got a little rotary encoder, and I can go red, and I can make it orange, and it can go white up to there. And this was just a little idle project to see if I could do it, but I don't know if you can see there. Hold on. So there's basically 2 red LEDs, and they will go up to full brightness, and then there's yellow LEDs that will come on as well, and then at the bottom, eventually white LEDs will come on as I turn them on as well. And those 3 LEDs are being pulse width modulated by just by software in actually written in Rust. I was going to say in C, but they were written in Rust, so it's just running a very tight loop, deciding which of the 3 LED channels should be on at any one time. And then a rotary encoder at the top, which is a super fun little swizzly device, swizzly control that will just turn around forever in both directions, and you can detect how much it's been turned. That was my... Oh no, I think I've broken it. Well, that's my latest little toy like project.
Cool.
I'm still looking to do something that doesn't involve LEDs. I'm not sure that will ever happen. I've kind of given up on that.
How would you know that it's on?
What?
How would you ever know whether it's on?
What? The LED, the non-LED project? Yeah, I don't know. Well, I did get, I got this for winter, and I haven't built it into anything. I got this. Spark Fun heating pad, which is you put 5 volts across it and it gets warm. And I wanted to build something with a temperature sensor to make it sort of try and keep itself body temperature, so I could stick it in my jacket and keep myself warm when I'm out in the cold.
I've got to say, Ben, I've built lots of projects like that. 5 volts and they get hot in no time.
Yeah. So what I don't want it to get too hot. I want it to be like the temperature of a warm dog or something is my goal.
Yeah, I guess carrying a warm dog all the time is not convenient, is it?
Yeah. It's inspired by carrying a warm dog. Every now and then I borrow my friend's dog, and she's lovely and warm. So all right. I'm gonna...
Ben, I've got a question.
yeah.
I'll put it in the chat. Are you using the same frequency when you're doing the pulse width modulation?
For what? For which project are you talking about?
Well, just say for just bringing on a single LED, just say a red LED.
Yeah.
You know, one about the brightness.
So you can use any frequency you want, and you can do it in some of the projects. It can be random. It doesn't even need to be regular, right? It just needs to be very fast. What matters is the changes are very fast, like more than 50 times a second, 20 times a second, and that the proportions of light are right. So one of my projects does it almost like a pseudo-random thing that I was experimenting with. Yeah.
No, the reason why I ask is normally when you think of your mains light, you'd think 50 hertz. But I tried doing an LED at that, and like you on about when you get your first from off, getting it to slightly come on. I changed the frequency, and I think I put it to about 100. And that first step of it getting it on made it much darker, if you know what I mean. So I was just checking if you'd changed the frequency or not.
Yeah, like I've played out with all different amounts to like basically, as far as I can tell, as high frequency as you can and as much resolution on the timing, you're going to get better control. Yeah. And whatever your device is, just pump it as fast as you can, you're going to get better resolution. That's how it's going to work, right? And as soon as you cut down on that, you're going to get less resolution.
Yeah.
I don't think there's anything more nuanced than that.
Ben, is it possible to control the brightness of LEDs using current limiting or some other technique?
Yeah,
have you tried about those sorts of things?
I was thinking about that today, because I was about to say you can only turn them on or off, and actually you can't. You can control the amount of current through them. Maybe I don't know enough about analog electronics to know what the circuit would look like for that. Because that
works fine.
You would turn it into telling that circuit what amount of current to let through, and so maybe you would then have the same problem, just one step removed. I'm not sure.
It does work fine. One place where it doesn't work is it works fine with pure color LEDs. Doesn't work with white LEDs.
Why?
Because the way that they're mixing they're really blue LEDs and phosphor, and you get the wrong ratio of color mix as you start to change the current through them. But for pure color LEDs, it's okay.
But your control circuit for that would still have to deal with being able to
I mean, you can change the brightness that way, but the color changes as well, is what I'm saying with the white LED.
Yeah, but even if it was a red LED, right? And you're trying to if you're trying to control a red LED from an Arduino or a Pi, right? And you're giving it a number from 0 to 255 or whatever, you would still have a problem with telling the current control circuitry.
You'd have quantization, and you'd
you'd have a quantization problem. Right? You'd have the same quantization problem.
But you wouldn't have the flickering in the same way.
Yeah, you wouldn't have the flickering. Yeah.
But your current controller is going to dissipate a lot of power unless you run it by pulse width modulating it. So you're probably not going to gain anything anyway.
Right, that's what I mean. Like, it's interesting to,
because you're trying to put a variable current through a device that basically has a constant forward voltage no matter what the current is. Not where it explodes.
Yeah.
Well, an LED doesn't have a constant forward voltage. It's
no, pedant mode.
It's not absolutely constant. Over quite a wide current range, you don't get much change in the voltage.
Yeah.
You know, the band gap, and that's what you're actually reflecting in the voltage.
Right. Yeah.
Be crazy to connect a little servo to a potentiometer just to control resistance.
That actually you would probably get very, very good the quantization on that could be amazing. Like the resolution on that.
Can even use a log pot to help as well.
Yeah. Oh, yeah. And they do faders like for mixing desks, right? That they look like.
They do, yeah, log faders.
Log faders, but they've got servos in them so that the mixing desk can move itself into the right place, but you still have.
Often for the group faders, they'll move all of the associated individual channel faders.
Yeah.
When you move the group fader, so you can then still trim the individual fades, but act as a group as well.
Huh. That's probably going to win the unnecessarily complicated LED control contest. Yeah. But like, if you're going really bright, you can put in 10 LEDs. Which someone was saying earlier, like you can put in multiple LEDs and control those LEDs. You're not controlling the brightness of one LED. You're controlling the brightness of your room, and your room is lit by 100 LEDs. But instead of controlling all of the LEDs together, you can control each LED individually. So you don't need the scale for each. You don't need the control for each LED so much. But you don't need resolution for each LED so much because you've got 100 of them. All right.